Hello everybody, welcome back. In this lesson, we will go over the complex plane and the geometric properties of complex numbers. So to begin with, first of all, we will start looking at the complex plane, the geometric properties, and then the polar form of complex numbers. So as a starting step, if you look at a complex number that we already know, we can indicate it in the Cartesian form, which means by indicating it in terms of x and y coordinate of the complex number, or more precisely, the real part and the imaginary part of the complex number. So when you talk about the real part, it is the real component x, and the imaginary part is exactly what is multiplied by I without including I. Now, we already know the modulus, or the magnitude of the complex number, can be represented geometrically by the quantity, the square root of x square plus y square, which is a natural consequence of, which is directly coming from natural geometric observation, and we indicate it by the absolute value sign. And then, based on this, the properties that can be used to describe complex numbers sometimes can be useful in computations. So the first one, we have had this observation already. When you consider the square of the absolute value, that is none other than the product of the complex number and its conjugate. And then that leads to the situation where whenever we need to compute the absolute value of the complex number, we can take the principal root of the product of the complex number and its conjugate. So why do we call it the principal root? Because when we consider the square root, there are two possibilities that we can think of even in the case of our real numbers. So for that case, we need to consider two possibilities, and we need to consider the leading possibility, which is exactly the principal square root, which is the positive square root of that number. And then the second component is about looking at the magnitude of z square. When you consider the magnitude of z square, that is none other than the square of the magnitude of that number. So in other words, it is coming directly from this product property. When you consider the magnitude of a product, that is none other than the product of the magnitude of those two numbers. Now, if you set these two numbers to be the same, you will get exactly this property, right? And then the same idea can be extended to the division of complex numbers. When you divide one complex number by another, and if you take the absolute value or the magnitude of it, right? So the precise word is not the absolute value, even though the notation is just like the absolute value, we call it the modulus. So the modulus of the division is going to be the divisions of the modular. So now let's look at the simple geometric properties, which we have already seen. However, we need to emphasize in certain computations. So when it comes to the complex plane, now if you consider two complex numbers, I will indicate the first complex number by x1 plus iy1, and then the second one, x2 plus iy2. Now, in this case, we can locate these two complex numbers by these two vectors. We can have this vectorial notation or vectorial symbol to indicate it, right? So now in the next step, if we try to come up with the summation of these two complex numbers, so that's none other than, it's a very simple geometric fact. what you're going to get is the addition of the x coordinates and the y coordinates. In other words, the addition of the real parts and the imaginary components. So that will result z1 plus z2, which is none other than x1 plus x2 plus I times y1 plus y2. Now, why is this significant? With that, we can see it is following exactly the triangle principle. So if you put these two into a triangle, so this is none other than z2, this one is none other than z1. And then when you set up the hypotenuse, that will direct you to the summation. So in that way, there's a nice geometric property that you can use in the scenario. So what about z1 minus z2? x1 plus iy1 should not be an equivalence. It should be just the addition, right? Now, when you consider the difference, which will be fairly straightforward, again, we are using the same idea. Now, if you're trying to compute z1 minus z2, first of all, minus z2 is none other than exact complex number in the negative direction. So pretty much like we extend this line with the same magnitude all the way to the other side. With the same magnitude. So this distance should be exactly same as the distance of the extended vector. Now, with that, if you consider, now this is negative z2, so that's going to be negative x1 minus I, so negative x2 minus iy2. Now we are going to use the parallelogram or the triangle principle just on these two numbers. So when you do that, you can recognize it's going to be exactly this. So that will locate, that will point us to this point where z1 minus z2 actually occurs. However, when you consider the magnitude of this number, you can recognize, or you can see exact length between these two in a different way. Look at this. This is parallel to exactly the line connecting z2 and z1. So z1 minus z2 can be recognized better by this. So that is the secondary diagonal that you see in the parallelogram if you complete that parallelogram. So the principal diagonal that you see here will provide the summation, and then the secondary diagonal, what you see right here, will provide you the difference. Right, so these geometric properties are going to help us in some computations related to the domains of complex numbers. So when it comes to complex numbers, we use the term domain interchangeably in different occasions. Sometimes we talk about domains of complex functions, but in frequently in many occasions we talk about domains of complex numbers, which is going to be a special subcategory or subtype, subset of complex numbers with specific properties. So we will talk about that more in detail later. Now, the next step. When it comes to the simplification, it is there are very important tools that we need to get to know. The first one is triangle inequality, because in many analytical properties, in many simplifications, you will see this is going to be a critical tool. So what is the triangle inequality? Now, we have seen the triangle inequality in terms of real numbers. So if you consider two real numbers, the summation, or like let's say the absolute value of the sum of the numbers will be less than or equals the sum of the absolute values of each number separately. Now, when you consider the real number line, actually this particular scenario, even though we call it the triangle inequality, you will not see the real geometric significance of that on the real number line because we are working on a line. However, when you consider uh, complex numbers, you can see exactly this idea. Now, to see that, what can we do here? Right. So let's get back to this picture. Let's have a quick visualization just to understand how and why this would work. If you can consider Z2 here and Z1, and then when you consider the summation that will be directed by this. Now think about this. When you consider a triangle, and this is the summation of the complex numbers, Z1 plus Z2. Now, if you focus on this triangle for a moment, you can see this is a triangle and the magnitude of Z2 is none other than the distance or the magnitude of this vector, and the modulus of the second complex number, which is Z2, that is equivalent to the distance of the second line segment or the second side of the triangle. Now, when you add these two sides, side number one and side number two, we can clearly see it is bigger than the third side, right? Or the um, right. So it is directly a geometric observation. However, those kind of geometric observations are not going to help you much when it comes to analytical properties. So you need to verify, you need to start from axioms of complex numbers or axioms of number systems. And that's exactly how you're going to develop these properties. Now, when I say that, when I provide you with that intuition, that is exactly going to tell you how to see this, but that's not going to exactly tell you how to prove it. So when it comes to the proof, you need to do some more work. Now, at this point, I will just provide it as a property, and I will point out where to and how to do the proof of that of this component, because it's a critical component in understanding. And then this result can be extended to n complex numbers. So in other words, if you take the modulus of the summation of n complex numbers, it's going to be less than or equals the sum of all the moduli of complex numbers that you consider. And then one more frequently used form of the triangle inequality is the reverse triangle inequality. Reverse triangle inequality, which can be directly processed by using or directly derived from the triangle inequality itself. How can we do that? Now, since we want to have some kind of like a rigorous mathematical reasoning background here, let's do this. Let's have a quick proof. Step number one, we already have the triangle inequality with us. Now, because of that, let's do this. z1. Now, if you consider z1 is none other than z1 minus z2, and then if you consider plus z2, right? So it is a very simple fact. Now, if you take the absolute value, or like let's say more precisely the modulus will give you again the modulus of the right hand side. However, now if you break the right hand side into two pieces by using the triangle inequality, because it's already available for any two complex numbers, so we can obtain this result. And then that simply means z1 minus z2, we can just subtract the same complex number, or like let's say we can subtract the same number from both sides. That will not change the inequality. Now what can we do? Now if you consider this form, look at this, compare it with what you need. What you need has an additional pair of absolute value. So in fact, the symbol that you see here around any complex number is the modulus. But what you see around this can be identified just as the regular absolute value, because you're dealing with two real numbers in this scenario. So, but at the same time, since you recognize real numbers are yet complex numbers, you can just treat this one as the modulus yet. Now, we do have everything in this inequality except for this, the missing component. So how can you introduce that? Now, sometimes in mathematics, we need to recognize exactly what we did, and we need to recognize the symmetry of the process that we did. Think about this entire computation, and there is no priority. I mean, there is no superior variable in this consideration. Z1 or Z2, both are exactly acting the same way. So if I just have the same formulation, I can say without loss of generality, one can say it this way, Z2 minus Z1. If we consider Z2 minus Z1 with the absolute values on the left side, that would be again the same thing as saying Z2 minus Z1 just by interchanging this on the other side. But then don't forget, you're considering the modulus here. It is just the magnitude of these two numbers. That magnitude would be same as the magnitude of Z1 minus Z2, the same quantity as before. So you can change the positions of these two numbers. And on the other hand, this number is none other than the negative of Z1 minus Z2 with the absolute value, right? So what you see here is essentially the same thing. So now if you look at these two pieces very carefully, you do have what you need. What is it? It is none other than a certain number. There is a number. There's a number in the right side. Now, for instance, for convenience, let me indicate it by some other notation. There's a number A. Since it's a real number, at the end of the day, I will just indicate it by A. This number A has these two amazing properties. This is greater than or equals some other number B, and at the same time, it is greater than or equals negative b as well. Now that simply means it doesn't really matter which sign you're going to assign to this number. A is always superior compared to the parity or the magnitude together with the parity of that number b. So that simply means even if you consider the absolute value, because absolute value of b is supposed to be one of these two possibilities, considering that it should be a real number. Therefore, if you get the absolute value of b, that should be less than, because there are two cases here, both cases are beating, in both cases a is beating the value itself or the negative value of b. Because of that, you end up getting this. Now that's exactly the observation that you want to have. Now this is not a part of the proof, therefore I'm just going to just have it as an illustration. So make sure to remove it from your consideration when you write the proof. But the role of this A is none other than this. The absolute value of Z1 minus Z2. And then the role of variable B is none other than exactly the role of this quantity that you're considering without the sign. So with that, now we conclude Z1 minus Z2. The modulus of Z1 minus Z2 is always greater than or equals the difference between the moduli of these two numbers and in fact the absolute value of that quantity. And this will play an important role in many computations related to continuity of complex functions and differentiability, and sometimes even analyzing the bounds. So triangle inequality together with the reverse triangle inequality will serve a greater purpose. Now, let's look at a quick example. Now, when you consider the circle, look at this. The absolute value or the modulus of z equals 2. What does that mean? Can you visualize it? Visualize that complex number or the possibilities for that complex number. So that simply means the magnitude or the modulus, that's a distance from 0 all the way up to that complex number. That distance is going to be 2, which simply means it is going to be a circle. And this complex number z is sitting on that, on the boundary, at the boundary of that circle, right? So it is exactly the boundary, one of the boundary points. Now, you need to consider an upper bound for this particular quantity. Now, it would not make sense if I ask you the same question in this way. Like if I remove these um, absolute value or the modular sign, and if I just leave it without having that, I mean, here we have a complex number. Now, we cannot just have an upper bound for a complex number because there is no natural ordering, because there are two dimensions in this picture. One cannot just say like, okay, one complex number is greater than the other unless you look at the modulus. So that's exactly the reason we have the modulus in this case. And then how do we analyze this? There are multiple steps that we need to have. Now, I'm showing you this computation at this point because these kind of computations will revisit us when it comes to analysis of convergence of complex sequences, or even in the situations of like establishing continuity of certain complex functions. You need to play with these estimates. So now, since the denominator is the leading component that we need to analyze here, I'm going to look at it first. And directly from the reverse triangle inequality, I can just make this one look directly like this. Z square. Let me use a different color so that I can have slightly different representation of this. So this is none other than z square plus 2z. Since we have plus, I'm going to make it a minus first, and then I'm going to say minus of 2z minus 5. You can do this. Now, this is just like your z1, and this is just like your z2 in the reverse triangle inequality. If you consider reverse triangle inequality, that is z1 minus z2, and that is always greater than or equals the difference between the moduli, right? And then minus, right? So you can always have this direction, and that's exactly what I'm doing here. So I take the modulus of each number separately, and when I do that, don't forget I have two negative signs inside this complex number, but since I'm taking the absolute value, that negative sign will be killed. And with that, I introduce the negative sign in between. And then now we have step number 1. Now, how can you work with step number 2? We need to further reduce it down to further level from here, from this step to the next. How can you do that? Now, that's exactly when you need to think carefully how you're going to use the triangle inequality. It is not the reverse triangle inequality anymore. We are going to use the triangle inequality carefully in this occasion. How could we do that? To do that, I'm going to have the direct version of this. So 2z plus 5 with the triangle inequality. Now I'm going to get less than or equals 2z plus the absolute value or the modulus of 5, which is none other than just 5. Now, what if I multiply this inequality by a negative sign? The reason is there's a negative sign right here. So what I can do in the first step is to multiply by a negative sign. So when I do that, I change the sign here. So let me change it to this. Now with the negative right there and with the negative in front of 5. So multiply the entire right hand side by negative. So that is what we end up getting. And then, in fact, there is a little bit of a jump here. It is inaccurate to have this one right here to compare. Before comparing it, we need to get rid of that absolute value, and we are going to do this. If there is a number, right? If you consider any, like let's say the absolute value of a number, that number is going to be always bigger than or equals the original number. So in other words, like if I just remove this, the outer modulus or the absolute value, then I'm going to get this. Should be just z square minus 2z plus 5. Now we get this, right? So simply, in other words, I just remove these two outer modular signs, and then I end up getting this. Now that's exactly when I would use the triangle inequality, not the reverse triangle inequality, is the regular triangle inequality you're using in this computation, and that will result this bound. And then once we reach that step, now look at this. We reach the level of z. And with that, we can use the assumption directly. The complex number z is assumed to be on the boundary, at the boundary of that circle with radius 2. So that gives us the value for these two, and now I can include them. So when I include z equals 2 here, I'm going to get 5, right? So we can just improve, right? So we can use the same. So that's going to be when you do this 2 times, right? So when you process that, you're going to get -5. This is not going to be +5, it's going to be a -5. But then don't forget, what we do here can be done in the same way in the reverse order. That simply means we can establish the fact that this is going to be exactly greater than 5 also. So that is exactly how we land on the combination, right? So once we have this term controlled, then you're trying to put that term in the denominator and you're trying to work with it. And in that way, you will get exactly the required inequality or the estimate for the given quantity. All right, so with that, we will move forward to talk more. Now, when it comes to these computations, you will see more of them like frequently when we try to analyze complex functions and complex sequences. So for now, we will keep it aside, and knowing that we would revisit those kind of computations. Now let's talk about a few interesting geometric and algebraic connections that we will be using in analyzing these functions. So the first, the polar form. We know the polar form because it's directly coming from geometry, right? So this is none other than the Cartesian form of the complex number. And then we know polar coordinates. So we are not going to call it the polar coordinates because it's the complex plane. But if you consider the similar configuration, you can see angle theta and radius r will point right at the same complex number z. It is lowercase z, I indicated in that form. And in that way, if you write down this x coordinate, that is none other than r cosine theta, and then the opposite side, which would be none other than y coordinate. So x is r cosine theta and y is nothing other than our sine theta. So that is going to be the y coordinate. Now put them together. And once you put them together in the position of x and y, then you're going to get the common term taken out, and then cosine theta plus I sine theta. Now, a couple of interesting things. Now, when you look at a complex number in this form, that geometric pattern, the geometric observation is going to say a lot. This part, this r is none other than the modulus of the complex number. And on the other hand, what you see on the second component right here, that is a number sitting on the unit circle. So you can always have the direction and the modulus of these two separated by this form. And then what is this theta? If you consider the role of theta, now this theta is not unique. Why it is not unique? One can say, like, let's say at a certain instance, it could be 30-degree angle. One can say like, oh, let's call it theta 0. And then somebody can just rotate another 360 degrees and catch the same orientation. That simply means 30 plus 360, or like 30 or pi over 6 plus 2 pi in radians. So it's going to be the same angle. If you have again another rotation, you're going to get the same orientation. So that simply means this angle theta is not going to be unique, and we will indicate it by, we will call that angle, we will give it a special name, we call it the argument. So ARG, and be very careful in this case, because when you write this notation ARG, do not write the uppercase in front unless you really mean it. Why? When we consider this lowercase arg or argument, that is identified as a multi-valued component. So when you write theta equals something here, theta equals arg z, theta is not going to stand only for one single value. It contains, it signifies, or it identifies a collection of values. There are infinitely many members in that collection. So in complex numbers, we will see this scenario frequently revisiting. There are certain relations that we call multi-valued functions. For instance, whenever we consider z, right? So what is this arg? So more precisely, all right, I will just indicate it in notation. This assignment, its arg is kind of like a function. It's a function notation that you see here. So arg is a function from the collection of complex numbers to real numbers. But this is not going to be a unique value. It is going to be, right? So arg z is going to be theta when z is r cosine theta plus I sine theta. But this angle theta is not uniquely determined. Therefore, I'm going to call this function, I'm going to say this assignment as a multi-valued function. It is very important that this is not even going to be a function in the conventional, when you consider conventional definition of a function. So, but when it comes to complex numbers or complex analysis, the complex world, or the realm of complex numbers, we frequently have this terminology in use. I mean, it has specific purposes. So we will see some of them in our upcoming conversation, but you need to make sure that this function, this assignment is not a single valued assignment. However, this is not really good in some computations. We need to recognize kind of like a principal value for this. So we are going to sometimes consider, like, other than lowercase, we will consider uppercase or uppercase arg of z. So what do we mean by that? It is also going to be an angle like this, theta, but it is going to be a very specific one. When you consider principal argument, so we call this symbol the principal argument. So this principal argument has the special property of being located between negative pi and positive pi, possibly including the positive pi, but not negative pi. So in simple terms, you're trying to recognize this quantity now between two values, right? So if you consider 30-degree angle, for instance, for convenience, I will talk about this in terms of degrees. And if you consider one complete round around it, you're going to get 360 plus 30. But once you consider 360 plus 30, it's not going to be sitting in this domain anymore, because this is 180, negative 180, this is positive 180. So that's exactly why we need to consider only one value here, that's going to be just the 30-degree angle, or in other words, pi over 6 in radians. So when we need to identify the angle, the polar angle of the complex number uniquely, we will consider the principal argument. All right, so now what is the connection? What's heading? Where are we heading with this, with complex number multiplication and division when it comes to operations? How could this geometric representation be helpful? This is what we're going to do. So when we have to multiply two numbers, so try to recognize the algebraic property behind this. Now, when you multiply these two, we are essentially multiplying these two components, the meaningful complex numbers here, and these two real components together, so R1 and R2. So when you consider the product of these two, you can see the output that you're going to get, Z1 times Z2 will definitely have, now this is the Z1 has the magnitude of R1, we'll call it the distance R1, and this is going to be R2. And when you consider Z1 times Z2, that will produce a complex number with the magnitude of the product of the magnitudes of those two separate complex numbers. But now, what would be the argument? Now, this is going to be a very simple observation if you recall the trigonometric observation behind this, right? So if you multiply these two components, this is what you're going to get. I will just write it down, and I will show you an easier way to understand this also that will require another tool. So when you multiply them, you're going to get R1 times R2, and then you're going to get cosine theta 1 plus I sine theta 1 multiplied cosine theta 2 I sine theta 2. Now, when this multiplication goes along, right, we know exactly how this is configured, right, the way that it's computed. So cosine theta 1, cosine theta 2, and then minus sine theta 1, sine theta 2, that is the product of the purely imaginary components, and then plus I times the cross terms. You're going to get sine theta 1 plus cosine theta 2 plus cosine theta 1 sine theta 2. Now, this is a simple observation that you need to have from trigonometry when you consider the summation of when you have cosine theta 1 plus theta 2. And if you expand that term, this is exactly what you're going to end up getting. And similar to that, if you consider sine theta 1 plus theta 2, if you expand it, this is what we would get. So in other words, this is the formula. This one is the formula for cosine theta 1 plus theta 2. And then I sine theta 1 plus theta 2 is the second component. So what we essentially get is this. The arguments, when you consider these two arguments, the argument 1, theta 1, and here we have theta 2, what happens when we get to the third argument is we are rotating. We start from theta to whatever the second number here that we consider according to this diagram, and then we measure another angle of theta 1 from there. So all together, what you're going to see is theta 1 plus theta 2. So this is important, because with this we can see, we can have this rough relation, like the connection, when you consider the argument of z1 times z2. That's nothing other than this relation. And of course, when you write down this statement, you have to be very careful, because we already know this argument of a complex number is a multi-value component. So because of that, you need to be careful. However, even though this would work in this way, it doesn't necessarily work when you consider the principal argument, because you restrict now. So stay with me carefully until the next step. I wrote equals here. Now I'm about to cross it. It's not actually equal in general. So what you need to do is to recognize, first of all, have this one as an observation and try to understand why it would work. And in the meantime, try to come up with a counter example for this. Counter example. What is a counter example? An example, like let's say example selection of Z1 and Z2, select two numbers in a way that the principal arguments of the product would not coincide with the summation of the principal arguments of those two numbers separately. So this is going to be much more easier than what it seems. All you need to do is to figure out two numbers and keep this in mind. The principal argument is supposed to be between negative pi and positive pi, possibly including the positive pi in the inequality. So keep it in mind and try to come up with a counter example for that. Now, with this, we we observe some of these properties. So let's think about the other scenario. Let's think about the other possibility. What would be the difference between this scenario and, like, let's say z1 minus z1 divided by z2? Now look at this. If you consider z1 divided by z2, what essentially happens is r1 cosine theta 1 plus r plus I sine theta 1, and then r2 cosine theta 2 plus I sine theta 2. Now, if you look at this combination, and you can clearly see R1 divided by R2 is going to stand for the magnitude of this number. And then you have this term in the denominator. But don't forget, whenever you have a complex number in the denominator, you have that simple trick. You can multiply by the conjugate of that number to bring that term to the numerator. So when you do that, don't forget, when you multiply at the bottom by the conjugate of this number, you're going to end up getting cosine square theta 2 plus sine square theta 2. That will result just 1. So when you do this multiplication, this is what essentially you're going to end up getting. You will have cosine theta 1 this times cosine theta 2 minus I sine theta 2, that is the complex conjugate. And at the denominator, everything simplifies out just to 1. And now if you simplify this term, this is pretty much the same formula that we had for the product, except for the negative sign that you see in the second number. So now when you multiply this out, you're going to get cosine theta 1, cosine theta 2, plus sine theta 1, sine theta 2, and then I, now the cross terms, sine theta 1 cosine theta 2, and then minus sine theta 2 cosine theta 1. Now, these two formulas would stand directly from trigonometry. All right, so since we already recall the formula for the summation, right, cosine of theta 1 plus theta 2, you can just adjust it little by putting a negative theta 2 in that picture, and that will give us this simple observation, r1 over r2, the modulus stays the same, and then you're going to get theta 1 minus theta 2 right here. And then the second angle is going to be, the second piece is going to be sine theta 1 minus theta 2. So in other words, when you do a division, what you're doing is essentially subtracting the arguments, which is exactly should tally with the observation that you had with the product. Now, that is one component. And then, is there a way that we can look at this in another way? Just in case if you do not recall, or if you do not like exactly this trigonometric approach, do we have another way to look at it? Now, yes, that is why the complex numbers are so rich in applications. Now, for instance, consider this representation of a complex number. You can have z, you can say x plus iy, Cartesian form, or you can have the polar form. The polar form can be represented in a different way by using Euler's formula, right? Cosine theta plus I sine theta, we have already seen this in a way, uh, kind of a hand waving argument that we had by then. And if you checked Professor Brunton's lecture that I shared with you, which is an excellent introduction, but yet I wanted to have it like in application orientation, it's a very good idea to have that intuition. However, it is not enough when you try to develop complex numbers from scratch as analogical objects. So we have to pay attention to minor details in this. Think about this scenario, right? So, yes, I mean, e to the I theta, in other words, e to the I theta is cosine theta plus I sine theta, right? Euler's formula or the Euler's relation, right? So we are already familiar with this. Already familiar with this with a hand waving argument because we pretty much like came up with that by using just Taylor's expansion and then separating cosine and sine and the imaginary components. But you should really understand there is a big gap in this consideration because we already know how to compute e to the something, right? E to the x when x is a real number, but we do not have an idea what it would be when you put just an imaginary number in that position. So this can be addressed in multiple ways. So one can simply say, oh, don't worry too much. Don't make it a big deal. Just put it there. Just write it like a power series. But the problem is How do you define it? Now, that is one of the things that we are going to have in the next step. When we think about like the definition of this function, e to the z, where z is a complex number, it is going to be a definition. And that definition comes with a historical conversation, the way that it was developed. So it is not going to be something straightforward. In construction, one cannot say like, oh, everything that you're going to see in real numbers should work in complex scenarios. No, it's not going to work. You will see many surprises. And we will leave this component as a further discussion or a point to ponder. However, at this point, I'm going to use this representation anyway because I want to make a point. What is it? If I consider z1, now we know we can represent it in this way. It's easy, right? z2, 2 e to the I theta 2. Now, this is the question that you should ask. If you get the product of these two numbers, that's now going to be R1, R2, and then the exponentials. And if we assume for a moment we have the same exponential rules in complex domain, that's going to give us exactly the summation of these two components, and that would be this. And that simply means the argument of this number, the product is going to be the argument of the summations of the arguments of those two separately. So the price that we had to pay in terms of trigonometric formulation earlier is now it's a void, right? Can you see? It is directly coming from this. But you may feel like, oh, this is magic. So this is great. But now that's exactly the difference between application-oriented viewpoint and the construction of knowledge. If if you're thinking about the construction of complex numbers as a theory, you need to see there's a huge component hidden behind this that we that we did not describe explicitly in this computation. So that's why this representation after the computation, it becomes so simple. But that does not mean it is elegant compared to the computational approach that we had before, because we are hiding too many facts. All right, so either ways, we can, now we have a better understanding by any chance if you consider z1 over z2, that's again straightforward. z1, r1 over r2, and then e to the I theta 1 minus theta 2. So feel free to use this in applications, but when you think about the development of this concept, always have that idea that it is not something obvious. We need to pay attention to minor details in that consideration, in that construction. So with that, actually, we are going to wrap up this conversation, and we're planning to discuss more about more simplifications that we can have in this bracket, right? So in this consideration, and then we are moving towards more interesting scenarios, which are exactly about functions that we can describe on top of these numbers. And that's exactly where our entire conversation will begin, actually. This is like, until up to this point, we're just trying to get familiar with the ways to manipulate these quantities. So we will meet with the next video lecture, and on that we will have particular geometric aspects that we're going to consider, and then we will jump right to complex functions. All right, so the homework assignments and the evaluation, like the homework together with the practice problems, will be posted on Bridgers. So make sure that you start right away, like right after having the lesson, start right away working with those problems. And in that way, you will have fresh memory, uh, and that will help you to work with these problems efficiently. All right, see you next time.